Welcome to another deep dive. This time, we're taking a closer look at barium.
Barium.
Yeah, barium. We've got some interesting excerpts from Wikipedia, the Royal Society of Chemistry, and even a scientific podcast.
Sounds intriguing. I have to admit, barium isn't an element that usually comes to mind.
I know, right? But it's actually more present in our lives than you might think.
Oh, really?
Yeah, from medical imaging to those vibrant green fireworks we all love.
Wow, I had no idea.
Trust me, this deep dive is going to reveal a whole new side to barium.
Okay, you've got my attention. Let's dive in.
All right, so first things first. Where does the name barium even come from?
Well, it actually comes from the Greek word baris.
Baries.
Yeah, which means heavy.
Heavy, huh?
And that makes sense when you think about it. Barium is a dense element, one of the densest.
So right off the bat, the name gives us a clue about its nature.
Precisely. And that density is actually key to one of its most important industrial uses.
Oh, let's hear it.
Oil drilling. You see, when you're drilling deep into the earth, you need a special fluid to help with the process.
A fluid. What kind of fluid?
It's called drilling mud, and it has to be heavier than the mud and rock they are breaking up down there.
Otherwise?
You risk a dangerous blowout,
Oh, wow. High stakes.
and that's where barium sulfate steps in.
Barium sulfate. How does it help?
Because it's so dense, it adds weight to the drilling mud, keeping those operations running smoothly.
So it's literally adding weight to the equation. I never would have guessed that.
It's pretty fascinating, right? But, the story of barium goes back even further.
Oh. How so?
Way back to the early 1600s, even before anyone knew what barium was.
No way. People were using barium back then.
Not exactly using it, more like observing it.
Observing it. In what way?
There were these alchemists in Italy near Bologna who were fascinated by these unusual pebbles they found.
Unusual in what way?
Well, they were smooth and they would glow.
Glow. What do you mean?
They would glow in the dark, for years, in fact, after being exposed to light.
Glowing rocks.
Yeah.
That sounds like something out of a fairy tale.
Right. The alchemists called them Bologna stones.
Bologna stones, huh?
And now we know those stones were actually barite, which is barium sulfate.
So they were unknowingly experimenting with barium all along. What a cool historical twist.
It really is, but it wasn't until much later that they figured out what was going on.
When was that?
It was 1772 when a chemist named Carl Scheele identified barite as containing a new element.
Ah, so that's when barium was first discovered.
Well, sort of. He couldn't isolate pure barium at that time.
What do you mean?
Well, it took another brilliant mind to achieve that. Humphrey Davy in 1808.
Humphrey Davy.
Right.
The same guy who isolated sodium.
Exactly. He used electrolysis, again, this time to extract pure barium from molten barium salts.
Davy, the element whisperer. Seems like he was behind so many key discoveries.
He truly was a pioneer. But let's get back to barium itself. We've established that it's dense, has a cool backstory, but there's more to it. Like what?
Well, it's highly reactive.
And highly reactive.
Oh, yeah. You'll never find pure barium in nature. It always wants to bond with other elements.
Well, it's not happy just being barium. It needs to be part of a team.
Exactly. It reacts quickly with air and water, and those reactions, well, they can be quite dramatic.
Dramatic. How so?
Take its reaction with water, for example. It releases hydrogen gas and a lot of heat.
Whoa, sounds a bit dangerous.
That's why pure barium needs to be stored very carefully.
Okay, so it's definitely not a loner in the element world. But how does that reactivity make it useful?
Well, it's the compounds that make it so versatile. It's all about teamwork.
Ah, so just like ingredients in a recipe, it's the combinations that make it interesting.
A perfect analogy. And these barium compounds, they have a surprisingly wide range of uses.
Like what? Give me some examples.
Well, we've already talked about oil drilling, but that's just the beginning.
What else?
Well, for example, barium is used in glass making and, believe it or not, fireworks.
Fireworks. How is barium involved in fireworks? You know those brilliant green fireworks that light up the night sky?
Yeah, of course. Who doesn't love those?
Chances are that vibrant green color comes from barium nitrate.
No way. So barium helps create those spectacular displays.
It does, and then you have barium sulfate, which is used in a completely different way.
How so?
Medical imaging. You might have even encountered it yourself if you've ever had a barium meal or a barium enema.
Now that you mention it, those terms do ring a bell. But wait, how can you ingest something with barium in it?
Well, the key here is that barium sulfate is insoluble.
Insoluble.
It means it doesn't dissolve in water. So even though many other barium compounds are toxic, barium sulfate is safe to ingest.
So it just passes through your system.
Exactly. It coats your digestive tract, and because it's so dense, it blocks X-rays.
Ah, so that's how doctors get a clear picture of what's happening inside.
Precisely. They can see the outline of your stomach and intestines, giving them a literal inside look.
Wow, so barium is helping doctors see what's going on inside our bodies. That's incredible.
It is, and this is just a glimpse into the fascinating world of barium.
It's definitely more than meets the eye.
And we're not done yet. Barium even plays a role in a field called paleoceanography.
Paleoceanography, that sounds intense.
It's the study of ancient oceans, and scientists use barium isotopes to understand past changes in ocean chemistry and productivity.
Okay, hold on. Back up a bit. What are isotopes again?
Remember how we said different isotopes of an element have slightly different properties?
Right, like different versions of the same element?
Exactly. And by analyzing the different isotopes of barium found in marine sediments, scientists can learn a lot about how the ocean has changed over time.
So it's like barium acts as a time traveler, carrying clues about the ancient oceans.
A perfect way to put it. And by studying those clues, scientists can learn about things like ocean circulation patterns, nutrient cycles, and even past climate changes.
Wow, so barium is not only helpful in the present, but also holds secrets about our planet's past.
It really is an element with hidden depths.
It's amazing how much we've uncovered already, and we're just getting started.
But before we move on, we should touch on the potential dangers of barium.
Right, you mentioned earlier that some barium compounds are toxic.
Exactly. While barium sulfate is generally considered safe, we still need to handle it with caution, and of course, only under the guidance of a medical professional.
That's a good point. It's a reminder that even seemingly harmless substances can pose risks if we're not careful.
Absolutely. And with that in mind, let's move on to the next part of our deep dive, where we'll explore even more fascinating applications of this multi-talented element. What we've talked about really is just scratching the surface. Barium has even more to offer, especially when we look at some of the cutting-edge research.
Oh, really? Like what?
Well, one area that's really exciting is its use in high-temperature superconductors.
Superconductors. Those materials that can conduct electricity with no energy loss.
Exactly. It's a pretty amazing phenomenon.
I remember reading about it. Yeah, it's like a superhighway for electrons, right?
Yeah.
No resistance.
Precisely. But the thing is, before certain materials were discovered, superconductivity could only be achieved at extremely low temperatures, close to absolute zero.
Yeah, that makes them pretty impractical for a lot of applications.
Right. But then materials like YbCO came along.
YbCO.
It stands for yttrium barium copper oxide. And it was a game changer because it was one of the first materials that could exhibit superconductivity at temperatures above 77 Kelvin.
77 Kelvin. That's still pretty cold, right?
It is, but that's the boiling point of liquid nitrogen.
Ah, so you could cool it down with liquid nitrogen, which is much easier and cheaper to handle than those ultra-low temperatures.
Exactly. That discovery really opened up a whole new world of possibilities.
I can imagine. But what kind of possibilities are we talking about? How could superconductivity change things?
Well, for starters, imagine a world with lossless power transmission.
No more energy wasted as heat in the power lines.
Exactly. Our energy systems could become incredibly efficient.
Wow, that would be revolutionary. What else?
Well, they also hold the potential to revolutionize energy storage. Imagine super efficient batteries that could store vast amounts of energy.
That would be a game changer for electric vehicles, renewable energy, so many things.
It would. And we can't forget about medical imaging. Superconducting magnets are already being used in MRI machines, and they provide incredibly detailed images of the human body.
It seems like superconductivity could touch almost every aspect of our lives.
It really does. And barium, as a key component in these high-temperature superconductors, is playing a critical role in making that future a reality.
It's incredible to think something we might consider ordinary, like barium, is at the forefront of such revolutionary technology.
It just goes to show we should never underestimate the power of scientific exploration. But speaking of barium's unexpected talents, there's another area where it shines: radiation protection.
Radiation protection. Wait, isn't lead used for that?
Lead is definitely a common material, but barium sulfate has some advantages in certain applications. Remember we talked about its density and its ability to block X-rays?
Yeah, that's how doctors can see the outline of our digestive system on X-rays.
Exactly. And those same properties, the density and X-ray absorption, also make barium sulfate a very effective radiation shielding material.
So it's like a lead apron, but for walls and equipment in places where radiation is a concern.
You could say that. It's used to protect people and sensitive equipment from harmful radiation. And what's great about barium sulfate is that it's less toxic than lead, so it's safer to handle and dispose of.
That makes a lot of sense. Safety should be a top priority when it comes to radiation.
Absolutely. But safety isn't the only advantage. Barium sulfate is also chemically inert.
Chemically inert, what does that mean?
It means it doesn't react easily with other substances.
Yeah.
So it's a more stable and durable shielding material than some other options.
So it's safer and more reliable, a win-win.
Exactly. Yet another example of how barium in its various forms can be used to protect us and improve our lives.
Barium is on a roll. But before we get too carried away, what about that barium titanate you mentioned earlier?
Ah, yes, barium titanate. This compound has some pretty remarkable properties, particularly in electronics.
Refresh my memory, what makes it so special?
Well, for one thing, it's an electroceramic.
An electroceramic.
It means it exhibits both electrical and ceramic properties.
Okay, interesting. So what does that actually mean in terms of real-world applications?
One of its coolest characteristics is that it's piezoelectric.
Piezoelectric. Now, there's a word I haven't heard in a while. Remind me what that means again.
It means that when you apply pressure to barium titanate, it generates an electric voltage. And conversely, if you apply a voltage to it, it physically changes shape.
Whoa, that's pretty wild. So you're saying it can convert mechanical energy into electrical energy and vice versa.
You got it. And this property makes it incredibly useful in a whole range of devices.
Like what?
Well, think about things like sensors, actuators, transducers, devices that convert one form of energy into another. Barium titanate is often a key component.
I can see the potential. Can you give me some specific examples? How do we actually use this stuff?
Sure. For instance, barium titanate is used in ultrasonic transducers, which are used in medical imaging.
You mean those ultrasound images that let you see a baby in the womb?
That's right. That's barium titanate in action. It's also used in sonar systems for detecting objects underwater, even in non-destructive testing of materials, where they use sound waves to find hidden flaws.
So it's helping us see things we couldn't otherwise see, both inside the human body and out in the world.
Exactly. And then there are sensors and actuators. For example, it's used in pressure sensors found in everything from car tires to aircraft.
Wow, so it's quietly working all around us, making things safer and more efficient.
It is. And what's really amazing is that scientists are still figuring out new ways to use it. They are even looking into using it for energy harvesting.
Energy harvesting, what's that?
It's about converting ambient energy, energy from things like vibrations or heat, into electricity.
So we might be able to power our devices using the energy all around us, thanks to barium titanate. That's incredible.
The research is still in its early stages, but the potential is there. That's what's so exciting about this field. There's always something new to discover. And speaking of discoveries, there's another barium compound we should talk about. Barium fluoride.
Barium fluoride. Okay, what's special about that one?
Well, unlike a lot of other barium compounds, barium fluoride is transparent to a wide range of electromagnetic radiation.
Electromagnetic radiation, you mean like light?
Yes, but not just visible light. It's also transparent to infrared light. Remember, infrared is the invisible light we feel as heat.
Right, like the heat from a fire.
Exactly. And because it can transmit infrared light so well, they use it to make optical components, things like lenses and prisms for infrared imaging systems.
So like it's helping us see the world in a whole new light. Or a new kind of light, I should say.
You got it. Think about thermal cameras, for example. They allow you to see heat signatures.
Right. Firefighters use those to see through smoke.
That's one use. But there are many others. Scientists use it to study the universe, engineers use it to inspect buildings, even the military uses it for surveillance.
Wow, so barium fluoride is helping us see the unseen.
It is. But let's switch gears for a moment and talk about barium and steel making.
Steel making, you mean barium is used in making steel?
It is. Adding a small amount of barium to steel, usually as part of an alloy, can actually improve its properties.
Really? How does that work?
Well, the barium acts as what they call an inoculant. It helps the steel form a more refined structure as it solidifies.
It's like a microscopic architect.
Exactly. And that finer structure makes the steel stronger and tougher.
So barium is helping us build stronger, more durable things.
Yeah.
That's pretty impressive.
It is. Just another way that barium is quietly influencing the materials that make up our world.
It seems like the list of ways barium is useful just keeps growing.
It's quite a versatile element. But before we get too carried away, it's important to remember that it's not all sunshine and roses with barium.
Right, we talked about the toxicity of some of its compounds.
Exactly. It's important to handle all forms of barium with care. Safety first.
Couldn't agree more.
And on that note, let's move on to the final part of our deep dive where we'll explore how they get barium out of the Earth and turn it into all these incredible materials.
Okay, so we've talked about all these amazing uses for barium, but how do we actually get it? How do they get it out of the Earth?
The extraction process. It's pretty interesting, actually. It all starts with mining barite, which, as you'll remember, is that heavy barium sulfate mineral.
Right, those barite rocks. So they dig it up. Then what?
Well, after they mine the barite, they have to process it. They got to remove impurities like quartz and other metals that might be mixed in.
How do they do that?
Usually they crush the ore first, and then they use a technique called froth flotation.
Froth flotation. What's that? Sounds bubbly.
It kind of is. Imagine a bubble bath for barite.
A bubble bath?
Yeah. They mix the crushed ore with water and some special chemicals, and then they bubble air through it.
And what happens?
Well, barite hates water, so it clings to those air bubbles and floats to the top.
Like it's trying to escape the water.
Yeah, exactly. And then they can skim off the barite, leaving the impurities behind.
Pretty clever. So now they've got their concentrated barite. How do they actually get the barium out of it?
That's where things get a bit more chemical. They have to convert the barium sulfate in the barite into barium sulfide.
Barium sulfide. Why?
Well, because barium sulfide is more reactive, easier to work with.
Okay, makes sense.
That's
But
it.
how do they do that? How do you change barium sulfate into barium sulfide?
They heat the barite with carbon, stuff like coal or coke, a process called reduction. They're essentially stripping away oxygen from the barium sulfate.
Ah, so they're giving the barium a bit of a makeover, getting it ready for its next role.
Exactly. And once they have barium sulfide, they can create all sorts of other barium compounds.
Like what?
Well, for example, if they react it with oxygen, they can get back to barium sulfate.
Wait, back to barium sulfate. Isn't that what they started with?
Yes. But this time, it's much purer. Perfect for things like medical imaging or those bright white paint pigments we talked about.
Oh, I see. They come full circle, but with a higher quality product. What about the other compounds, like barium carbonate and barium nitrate? How do they make those?
They react the barium sulfide with other chemicals, depending on what they want to make, and they can even get pure barium metal.
Really? How do they do that?
It usually involves a bunch of reactions, often starting with barium oxide and aluminum. It's a bit more complex, but it gets them to that pure element in the end.
It's amazing how much goes into getting barium from the ground to all its different uses.
It really is a real testament to the creativity of chemists and engineers.
Speaking of creativity, we talked about barium's role in paleoceanography, the study of ancient oceans. Can you tell me a bit more about how barium isotopes help us understand past climates?
Oh, absolutely. It's actually pretty fascinating. You see, different isotopes of barium exist in nature, and the relative amounts of those different isotopes, well, that can tell us a lot about how they were formed.
So it's not just about whether barium is present, but about which specific types of barium are there.
Exactly. Scientists focus on the ratio of barium-138 to barium-137 in marine sediments. This ratio, it's influenced by a lot of things, like the amount of barium coming in from rivers or from those hydrothermal vents on the seafloor, even the breakdown of certain minerals.
Okay, so a lot of factors can affect that ratio.
Right. And by analyzing these ratios in those ancient sediments, they can figure out how barium has moved through the ocean over time.
So they're like little fingerprints, those ratios.
Yeah, exactly. And it gets even cooler. Barium, it can get incorporated into the shells of some marine organisms. And those shells, they become like tiny archives, preserving the barium isotope signature of the water those creatures lived in.
So it's like they're capturing a snapshot of the ocean at that moment in time.
That's a great way to think about it.
Mm.
And then scientists can analyze those ancient shells, see what those ratios are, and get a glimpse into the ocean's past.
What kind of things can they learn from that?
All sorts of things. They can learn about how the ocean circulated, how many nutrients were available, even how the global climate was changing.
Wow. It's like a time machine for the oceans.
It really is. And it all comes down to those barium isotopes.
Yeah.
It makes you wonder what other secrets are hidden within the elements around us.
This whole deep dive has been incredible. I've learned so much about barium, things I never would have imagined.
It's been my pleasure. It just goes to show that there's always something new to discover, even about the things we might take for granted.
Absolutely. And to our listeners, thank you for joining us on this journey into the world of barium. We hope you've enjoyed learning about this versatile element, from its hidden roles in our everyday lives to its potential to shape the future. Until next time, keep exploring.